Hello, my name is Michelle Donegan. I am a radiation engineer and supervisor of the Space Environmental Effects Engineering Group at the Johns Hopkins Applied Physics Laboratory. Let's transition to discussing the radiation environment on the lunar surface. The main sources of ionizing radiation on the Moon are galactic cosmic rays, GCRs, and solar energetic particles, SEPs. GCRs are highly energetic charged particles accelerated in space during the core collapse of supernovae. GCR energy spectra for protons and heavy ions peak at energies as high as 1,000 MeV per nucleon and can extend to hundreds of giga-electron volts. SEPs occur sporadically and are generated at the sites of solar flares or by shock waves from coronal mass ejections. These events produce particles including high-energy protons, electrons, and heavy ions. The flux and effective dose rate on the Moon from these sources is about half that in deep space, due to the self-blocking by the Moon itself. These effects still pose a threat to electronics, hardware, and astronauts. Of less risk on the Moon are albedo particles, mainly neutrons, which are produced by the interactions of GCRs and SEPs with the lunar surface material. Sources of ionizing radiation are common for space-based missions, and even for pilots high above Earth's surface. The annual estimated dose varies according to the particular location. The ionizing radiation environment is also cumulative. The more time an object or a person is in space, the more dose it will accumulate. The table on the right compares the lunar surface environment to other common environments for space-based missions. Satellites in low Earth orbit are expected to experience about half a kilorad per year, for example, while those in geosynchronous orbit are expected to experience approximately 40 kilorad per year. Each of these doses are for a shielding level equivalent to 100 mils, 1/10 of an inch, of aluminum. The same hardware on the lunar surface, with the same equivalent shielding, could be expected to receive 2 kilorad per year of dose from ionizing radiation. The effects of ionizing radiation pose challenges for hardware, electronics, and photovoltaics, as well as threats to human health. Ionizing radiation may impact the chemical structure of non-metallic materials, leading to discoloration, loss of strength, and embrittlement. These degradation mechanisms must be accounted for when considering, for example, selection and material lifetime for optical materials and coatings, structural materials, and so on. Ionizing and non-ionizing radiation can degrade the performance of electronics and photovoltaics, making them less efficient and effective over time, and in some cases resulting in permanent part failure. While hardware and electronics can be repaired and replaced over time, the impacts to human health are more difficult to overcome. Radiation is known to cause physiological effects in human beings, including neurological disorders, nausea, fatigue, and higher lifetime risks for cancers. Since the lunar radiation environment is more severe than that on Earth, it will be important and challenging to establish adequate protections against overexposure. A variety of tools and strategies already exist to help us define and understand the radiation environment on the lunar surface. A wide variety of modeling software packages are available, depending on the approach and output of interest. Some of these can be used or downloaded for free, for example, SPENVIS, while some require a free software authorization request via NASA, such as Ulteris. Still others require purchase of a license, such as FastRad. The complexity and barrier to entry for tools and software packages ranges from relatively easy to use, out-of-the-box engineering tools to very complex nuclear physics tools that were developed for the nuclear effects communities. Simulating the lunar radiation environment in a test facility can provide a unique opportunity to collect data on the response to radiation of a wide variety of parts, hardware, and materials in different configurations or operating modes. It is often possible to accelerate exposure, allowing for predictions of end-of-life degradation after hours, months, or years in space. While the radiation on the Moon's surface can't be avoided entirely, there are strategies for tempering the effects, such as strategically introducing particle-specific shielding or implementing conditional operating modes that can reduce either the likelihood or the magnitude of degradation experienced. In some cases, shielding can block particles entirely, or it can reduce the amount of radiation that is experienced over a given time. For example, as mentioned earlier, a spacecraft in GEO will receive approximately 40 kilorad of dose per year with shielding equivalent to 100 mils of aluminum. If that aluminum shield thickness is increased by 5 times, the annual dose drops by a factor of nearly 100. In most cases, the lower dose has the advantage of significantly increasing a part's usable lifetime in GEO. The reduction here is specific to the charged particle environment in GEO, and other orbital locations will experience different benefits from specific changes to shielding thickness. Conditional operating modes, such as reducing power, turning off non-essential electronics, or sheltering in locations with heightened shielding, can be advantageous in response to solar energetic particle events, such as those associated with a solar flare. These strategies can help avoid exposure to a temporarily more severe radiation environment, or avoid operating electronics in a vulnerable state. Best practices for electronics include other mitigations, such as redundancy, latch-up protection, and filtering. Listed here for reference are a number of standards relevant to definitions of the space radiation environment and approaches for analysis, test, and mitigation. They span NASA, U.S. military, the European Space Agency, and international standards organizations.